Okay, so we're continuing on into 11.4 now. This is hypothesis testing for two population proportions. So as we've discussed in the last 3 lectures now, the objectives don't change. We need to look at the test statistic and the rejection regions. Excuse me. And then we can take a look at running the hypothesis test on two population proportions. So these are proportions. So in our test statistic, we have our usual requirements. N1 P1 hat needs to be bigger than 5. N1 times 1 minus P1 hat needs to be bigger than 5. Remember, this is number of successes needs to be bigger than 5, and number of non-successes or failures needs to be bigger than 5 in both samples, both sample 1 and sample 2. And then the test statistic for two population proportions is a z-score. And this is P1 hat minus P2 hat, parentheses, minus P1 minus P2, all over the square root of P bar times 1 minus P bar, and this is times 1 over N1 plus 1 over N2. Now P bar has a special equality. P bar is equal to x1 plus x2 over n1 plus n2. So, of course, x1 and x2 are the number of successes in population 1, population 2, respectively. P1 hat, P2 hat are the sample proportions for samples 1 and 2, and then P1 minus P2, this is the estimated proportional difference that we get from our null hypothesis, as we always do. P bar is a type of average. It has a name, and I am blanking on it for some reason. I think, what was it? It's called the weighted estimate of proportion, I believe is what it's called. So it is a type of average, but it is essentially assigning the correct weights to the two number of successes using our sample sizes. We're not going to go into too much about P bar. We're just using it for this statistic here, this standard score Z that we've been calculating. So next we want to identify our hypotheses. Of course, there are always 3 versions. The left tail test, our null hypothesis, would be that P1 minus P2 is greater than or equal to 0. Our alternative then would be that P1 minus P2 is less than 0. For the right tail test, our null hypothesis is exactly the opposite of this one. It would be that P1 minus P2, I forgot the minus sign in there. Let's just rewrite that. P1 minus P2 is less than or equal to 0, and the alternative then is that P1 minus P2 is greater than 0. And for the two-tailed test, H0, P1 minus P2 is just that it is equal to 0, and our alternative then is that P1 minus P2 is not equal to 0. And just as a little reminder, this is z-score, so we can use the p-values really easily, calculating our p-value from the standard score tables or using the calculator. So let's take a look at an example. Oh, I skipped the rejection regions. That's right. So the rejection regions are the same as all z-scores are. If it's less than z sub alpha for the left tail test, then it's rejected. If it's greater than for the right tail test, it's rejected. And if it's the absolute value. The same regular rejection regions we have as in 11.1, where we look at those because they are z-scores. We're still using the normal distribution. So let's take a look at this example. A politician is looking at the effect of a recent policy change on her approval rating. Before the change, 480 out of 1,200 approved, and afterwards, 550 out of 1,180 approved, using a 5% level of significance test if the approval rating increased. So, as is tradition, we identify our hypotheses first. So we are testing if there is an increase, which means we want to know if the proportion, because that's what these are, performance ratings are usually proportions. P1 minus P2. Did it increase? So we would look at, is it less than 0? Now, why would we look at that? Because if it increased, then P2 would be greater than P1. So you can translate this as P1 is less than P2. That would be an increase. I know a lot of times we think increase, and so the most common error is to make this a greater than, but remember, it's always in relation to each other. So we're saying the second round would be bigger. And that means that our null hypothesis would be that P1 minus P2 is greater than or equal to 0, in which there was no change or approval was higher before the policy change that was enacted. So P1 hat, this is 480 out of 1200. N1 is then 1200. P2 hat is 550 out of 1180, which makes N2 equal to 1180. And our requirements, N1 P1 hat, this is 480 over 1200 times 1200, or 480. The other one, so that one's bigger than 5, that's good. N2 P2 hat, this is going to be 550. And we're going to shortcut this a little bit. The N1 times 1 minus P1 hat is just the opposite of 480. And that's going to be 720 to add up to 1200. And N2 times 1 minus P2 hat is the difference between 550 and 1180, which is 630. All of these are bigger than 5, so we are okay to continue. So let's go ahead and walk through this one using just the standard score. So we would need to calculate P bar, which is x1 plus x2 over n1 plus n2. And so that would give us 480 plus 550 over 1200 plus 1180. And this as a decimal, 0.432773. Remember, I believe I said in an earlier section, if you're going to do these intermediate calculations and you're not going to use the exact fraction, which of course we could, being 1030 over 2380, round it off to at least 6 decimals. You want to try and minimize the number of rounding errors that you introduce into your calculation. And then our z-score then, plugging into our values, we have 0.480 over 1200, is a nice round decimal, minus 0.466102. This is an approximation of P2 hat. And then this is going to be minus 0. That's coming from the null hypothesis. All over the square root of 0.432773 times 1 minus 0.432773 times 1 over 1200 plus 1 over 1180. And this is all coming out to negative 3.25. This is a z-score, so we can round it off to 2 decimals. Now, if you want to use all the fractions in here, your number might differ by a decimal place or less. All the difference you most likely will see past the second decimal when you round it. And the reason we're doing it this way is just to remind ourselves, if we want the probability, since this is a left-tail test, we want the probability that z is less than or equal to negative 3.25. In our z-score, either using the calculator or looking at the tables, we get 0.0006. This is, of course, less than or equal to 0.05, our alpha value. And when we're less than our alpha value, we always reject the null hypothesis. H naught. And so what does this mean? This means that there is sufficient evidence that the approval rating did increase. Now, this is, of course, only at this significance level of 0.05, our alpha value. And it does not tell us how much it increased. In fact, you can look at the raw data here, 480 out of 1200, 550 out of 1180. We're looking at 0.4 versus 0.46, so not even a full percentage point. But this is something that you would look at if you were comparing one set of approval ratings to another. Okay, so let's take a look at 11.4's last example. So this says the number of driver's education tests from 2 different driving schools are listed. So school 1, we have 17 that passed, 8 that failed. School 2, we had 23 that passed and 6 that failed. And we're going to use a significance level of 10% and determine if the population proportions of passing tests are different. So this is a two-tailed test because we're just looking at, are they different? So that means P1 minus P2 for our null is that they are equal to 0, i.e. they are not different. And our alternative is that P1 minus P2 is not equal to 0. Our alpha value is 0.10. Our N1, adding up these two things, is 25. Our N2, adding up these two, is 29. So that means P1 hat is 17 out of 25. P2 hat is 23 out of 29. And we can see that the number of successes are all greater than 5 here. If you want to write that in, they're all bigger than 5, just barely on this one. So we can go ahead and move into our calculation. So again, if you're going to do this by hand using the p-value and standard scores, make sure you calculate your p-bar, which comes out to 40 over 54. But if we want to do this in the calculator, we go to Stat, scroll over to our tests, and we are picking the option that is a 2-prop z-test. So we want to make sure that we enter our info, x1 being 17, n1 being 25, x2 being 23, and n2 being 29. Make sure that you select the p2 is not equal to, because that's what it would be if we move this over. So make sure you pick the not equal to, and then hit calculate. And so the screen that we see should give you a z-score of approximately negative 0.95. Rounding off to 2 decimals, it should give you a p-value of approximately 0.344, rounding off to 3 decimals. And so we can use the p-value or we can use the z-value. Again, I tend to like p-values because it's simpler than having to go find a critical z-score. Comparing this to 0.10, our alpha, this is greater than, so we fail to reject the null hypothesis. Because we are in the body of the distribution, we're in that center. And so this means for this particular scenario that there is not sufficient evidence to conclude these schools have different passing rates. Or I guess we should say proportion to make sure we don't imply anything else at this significance level. Now you notice I sometimes don't say at this significance level. Typically when you are rejecting your null hypothesis, you can leave that off because you are saying that the test that you ran says rejected. And so if someone wants to know what significance that level was, they go, look, this leaves a nice, clear instruction that while we cannot conclude the schools have different passing proportions, we could change the significance level. Or we could go to 0.05, we go to 0.01 and see if that is in fact the case. But fairly straightforward. 11.4 is not too bad of a section. The next section, 11.5, a little more complicated. We'll get there in the next video.